Good day. We are the Group 4 from PUP, specifically from BSEE 33. So, ang topic namin po ngayon is the branch circuit and overcurrent protection and arc flash analysis. Ngayon, ako ang magtatakel and magrepresent ng branch circuit and overcurrent protection. Bago ang lahat, bakit nga ba natin kailangan pag-usapan yung mga ganitong bagay? Bakit kailangan natin itong i-topic? So, syempre, sa mga plano, sa mga project, gumagamit tayo dyan ng mga protective devices like circuit breaker, for example. Kailangan natin pag-aralan yung ganitong computation to ensure the safety of people para ma-prevent natin yung mga aberya, yung mga dangerous na mangyayari. Kaya kailangan natin i-rate yung circuit breaker precisely and accurately dahil may mga nakasalalay na buhay doon. So, kailangan mas makuha natin yung accurate and precise na rating para gumana yung circuit breaker, yung certain circuit breaker na yon sa most efficient way na purpose niya. Since dito nga sa MMDA Pandakan, gagamit tayo ng iba't ibang kinds ng circuit breaker or protective devices. So, next is gagamit tayo dito ng MCCB, which is for longer term molded case circuit breaker. Ano nga ba ang functions of MCCB? So, nakalagay po dito for electrical fault protection, protection against overload, switching the circuits on and off. So, ano nga ba ang itsura ng MCCB kung naka-curious kayo? So, ito ang itsura ng MCCB. Yan. Meron po tayo dyan naka-provide na picture. So, MCCB is mainly used for both low and high braking capacity requirements, mainly industrial. So, ayan. Which is tayo rin, gagamit rin tayo nito sa ating project na ito. So, next is the safety switch. Ano nga ba purpose of safety switches? Disconnecting means for service entrance, tapos fault protection for motors. Okay, let's proceed. Ito ang itsura ng safety switch. So, kung makikita natin, evident na parang may takip siya. Bakit nga ba? Sabi dito, the enclosure provides a degree of protection to personnel against incidental contact with live electrical equipment. So, ayun, gagamit rin po tayo nito. So, next, itong formula na ito, parang need natin to i-keep in mind dahil kumbaga, ito yung puso ng computation natin, which is the base current is equals to base power all over square root of 3 multiplied to base voltage. So, kung nagtataka kayo, bakit meron square root of 3? Dahil nga po, 3-phase. So, ang formula na ito, ang reference ko po dito is the electrical design analysis, voltage drop, and short circuit calculations by Alcasabas po. Okay? Ito nga. So, IF is equals to kVA all over kV times square root of 3 times 1.25. So, where yun, current in feeders, yung IF, kVA, base power in kilovolt ampere, kV, base voltage in kilovolt, line to line. Tapos yung 1.25 is the 125% sizing for the overcurrent protective device. So, may pagganon po tayo para yun yung protection para sa ating circuit breaker kung sakali kaya may parang pasobra. So, next, dito sa part na to, ang gusto ko lang i-highlight dito is itong unang part lang na to. Ayan. So, ito. Paano nga ba nakuha yung 4.7 current na to? So, di ba nga, katulad dun sa ating formula kanina, para makuha natin yung current is yung kVA 1.5 over voltage which is 230 volts, 230 times square root of 3, tapos yung 1.25 na pasobra natin. So, doon natin makukuha yung 4.7 na current. Dito, mayroon naman ng list of current na dito sa schedule of loads na to ng MCC panel existing sa MMDA Pandakan. So, ayan, meron naman na po. Meron na nakalagay dito mga currents. So, ayun, pinakita ko lang kung paano yung naging computation ng bawat part na yan. Let's proceed lang sa dulo. So, ito ang gusto ko lang pong i-point out, which is the total. So, sa dulo, since meron na nga po tayong given current dito dahil nga na computation based on our formula, ang ating total current is the 196.5 amperes. So, kung titignan po natin, di ba, gumamit po siya ng 3.3 pole double throw safety switch. Ayan po. Pupunta tayo nga ito nga po sa ating computation. So, kung makikita natin yung schedule of loads kanina, ito po yung naging computation. In total rin po ng kVA, papalo po siya ng 63.9 kVA. Tapos, papalo rin po siya ng, ayun nga, yung 196.5 amperes, tapos 230 volts. So, para makuha natin yung so, summation of load amperes lang naman, 4.7 amperes plus 4.7 amperes plus 3.3 amperes plus 3.3 amperes plus 1.9 amperes plus 8.5 amperes plus 4.7 amperes plus 8.5 amperes plus 8.5 amperes plus 8.5 amperes plus 7 amperes plus 8.5 amperes plus 8.5 amperes plus 18 amperes plus 8.5 amperes plus 14.1 amperes plus 13.8 amperes plus 4.7 amperes plus 1.9 amperes plus 14.1 amperes plus 13.8 amperes plus 18 amperes plus 6 amperes plus 3 amperes. So, which magto-total sa 196.5 amperes, which is nag-satisfy naman. So, to get the circuit breaker size, so itong I natin, 196.5, plus the highest ampere in a motor, i-multiply natin sa 0.25. So, ano nga ba yung I natin, 196.5, tapos ang highest ampere in motor natin is the 13.8. Tapos kapag binultiply natin sa 0.25, makakuha tayo ng 199.26 amperes. Since nga doon pa lang sa computation natin, nag-add na tayo ng 1.25 for the protection of the protective device, gagamitin natin is the 200 ampere trip na 3 poles double throw safety switch. Ayun lang naman po. So, for next, ito naman, basically, ito po ang summary ng ating schedule of loads na una, which is the existing na MCC panel. So, makikita natin yung Metro Manila Development Authority, which is MMDA. Kung makikita natin, ito yung mga values ng una. Tapos, humalo tayo sa 199.95. Ito yung na-compute natin na. So, ito yung total of amperes lang. Tapos, ito yung may computation na po, yung 199.95. Makikita natin dito na ang magagamit natin dito is the 200 ampere trip safety switch, which is nag-satisfy naman sa ating computation. So, basically, yan lang po ang ating summary for that matter. So, next. So, dito naman, branch circuit breaker computation naman ng MCC. Ito naman yung proposed na schedule of loads. Gusto ko lang pong i-point out dito yung total, which is the 744.1 at saka syempre 460 volts natin dyan. So, paano nga ulit natin makukuha yung current? Ito, example na natin itong circuit number 1. Di ba nga sinabi, to get the current, gagawin natin dyan is kVA over yung voltage 460 times square root of 3. Tapos, syempre, i-multiply natin sa 1.25. So, ayun, magsasatisfy po, which is makukuha tayo ng 245 amperes. So, ayan. Tapos, ito lang naman po yung total natin, which is the 744.1. So, mag-proceed na po tayo sa ating computation. So, ito naman po ang computation natin from MCC proposed. So, as we can see, to the previous schedule of loads, nakikita po natin doon na ang total kVA is 387.4 kVA. Tapos, syempre, in-highlight ko rin po kanina, mayroon po tayong 744.1 amperes, tsaka syempre 460 volts. Ayun nga, dahil nga meron na po tayong parang list of currents doon sa schedule of loads natin. So, basically, ang gagawin na lang po natin is isa-summation yun. Dahil nga dun sa tinuro ko nga pong formula, dun nakuha yung mga currents. So, since given naman na, So, magiging I natin is summation of load amperes, which is 245 amperes plus 245 amperes plus 94.1 amperes plus 160 amperes. So, magto-total tayo ng 744.1 amperes. So, to get the circuit breaker size, so I, which is, ayan na nga po, 744.1 amperes plus highest ampere in a motor times 0.25. So, gagawin natin is 744.1 amperes plus 245 amperes times 0.25. So, makakuha tayo dyan ng 805.35 amperes. So, dito, based nga rin po dun sa ating schedule of flows, gagamit tayo dito ng 1,000 ampere trip, 460 volts, triple MCCB, which is the molded case circuit breaker. Okay, for next, ayun nga, katulad nga po ng kanina, meron tayong summary ng ginawa natin, which is the MCC proposed. So, ayun nga, katulad nga po kanina, ito nga po yung highlight natin, which is the total KVA. Tapos, nagkaroon tayo ng yung amperes. Ito yung na-compute natin kanina, which is pumala tayo ng 805.35 amperes. So, as we can see here, gagamit tayo dito ng 1,000 ampere trip MCCB sa ating main breaker. So, ayun lamang po. Next is the arc flash analysis and calculations, and ayun lang yung sa part ko, which is the branch circuit and overcurrent protection. So, for the arc flash analysis and calculations, it will be discussed by my partner. So, ayun lamang po.
Now let's go to arc flash analysis and calculations. So this is the summary of fault values. This is the fault numbers. This is their corresponding fault current in the unit of ampere. So this is the arc fault current formula. This is the formula. Where log 10, if under 1 kilovolt system, this is the formula to be used. If over, this is the formula to be used. Where log is the log 10, IA is the RC fault current in kiloampere, K is negative 0.153 for open configuration, and negative 0.097 for box configuration. The short circuit current is the three-phase fault, symmetrical RMS, it should be in kiloampere, all the voltage fault current. V is the system voltage, G is the gap between the conductors. Incident energy En normalized at 610 millimeter and 0.2 seconds. This is the formula to be used. Where log En, this is the formula. Incident energy E at working distance, this is the formula to be used if the system voltage is under 15 kilovolt. If over, this is the formula to be used. Where En is the normalized incident energy, it should be in joules centimeter squared. CF is the calculation factor, 1.5 for volt of 1 kilovolt or less. If above 1 kilovolt, the calculation factor is 1.0 or 1. D is the working distance from the arc source, it should be in millimeter. T is the RC fault current, it should be in seconds. X is the distance exponent that can be seen in the table 8.17. So this is the hazard risk category matrix. This is both minimum incident energy, where this is the scale 0 to 1.2, 1.20, 1 to 4. So this is the risk category for PPEs. This is the required minimum rating of PPE based on calorie per centimeter squared. This is the values. Case number 2, fault number 1. This is the genset or generator set. First step, determine the voltage fault current or short circuit fault current, which is 188.266 kiloampere. Next step, we determine the arc fault current. So this is the formula. This one, we have a separate formula, which is this one, to be substituted by these variables. Now we substitute the variables we have earlier. The value we get is this one. Then we solve for IA. We got 32.192 kiloampere. This is our RC current. Determine the incident energy and that is normalized at 610 millimeter at zero point 0.2 seconds. So this is the formula. The formula for log En is this one. Substituting the variables, we got this one. Solving for En, we got 9.758 joule per square centimeter or 2.331 calorie per square centimeter. Now we determine the incident energy E at working distance. So this is the formula. Substituting again the variables we got. The answer is 15.852 joule per square centimeter or 3.787 calorie per square centimeter. And use category 2 PPE. Now we determine the R plus the boundary dB in millimeter. The value of EB is 5 millimeter. Substituting the variables in this formula, we got 919.154 millimeter. Moving to the fault number 2, we determine the voltage fault current or short circuit fault current. We got 64.099 kiloampere. So this is the formula again for RC current. And this one. So this is the variables we use. Substituting the variables we have, we got this one. Solving for IA, we got 14.908 kiloampere RC current. So do we determine the incident energy En that is normalized at 610 millimeter at zero point 0.2 seconds. So this is the formula, log En. So this is the formula for log En. Substituting the variables we have, the log En, we got this one. Solving for En, we got 4.246 joule per centimeter or 1.014 calorie per square centimeter. Determine the incident energy E at working distance. So this is the formula. Substituting the variables again, we got 6.898 joule per square centimeter or 1.648 calorie per square centimeter. We suggest using category 2 PPE. Now we determine the R flush boundary dB. It should be in millimeter. So the value of EB is 5 millimeter. So this is the formula. Substituting the variables we have, the answer is 553.565 millimeter. Now let's go to fault number 3. First step, we determine the voltage fault current or short circuit fault current, which is 79.195 kiloampere. We determine the arcing fault current by these formulas using the variables we have. Now substitute the variables. We got this one. Solving for IA, we have 17.339 kiloampere as our arcing current. Now we determine the incident energy En that is normalized at 610 millimeter at zero point 0.2 second. This is the formula for En. The formula for log En is this one. Substituting the variables we have, the result is this one. Solving for En, we got 4.999 joules per square centimeter or 1.194 calorie per square centimeter. Next up, we determine the incident energy at working distance. This is the formula to be used. Substituting the variables we have, the answer is 8.121 joule per square centimeter or 1.94 calorie per square centimeter. We suggest to use category 2 PPE. Now we determine the R flush boundary dB. It should be in millimeter. The value of EB is 5 millimeter. So this is the formula to be used. Substituting the variables we have, the answer is 611.471 millimeter. Now let's go to fault number 4. We determine the voltage fault current or short circuit fault current, which is 19.113 kiloampere. Now we solve for arcing current. So this is the formulas to be used. This is the values. Now we substitute the values to the formula. We got this one. Solving for IA, we got 6.279 kiloampere as our RC current. Determine the incident energy En, that is normalized at 610 millimeter at 0.2 second. So this is the formula. The formula for log En is this one. Substituting the variables we have, the result is this one. Solving for En, we got 1.667 joule per square centimeter or 0.398 calorie per square centimeter. Now we determine the incident energy E at working distance. This is the formula. Substituting the variables we have, the result is 2.708 joule per square centimeter or 0.647 calorie per square centimeter. We suggest to use category 1 PP. Now we determine the arc flash boundary dB in millimeter. The value of EB is 5 millimeter. So this is the formula. Substituting the variables we have, the result is 313.135 millimeter. So this is the summary of arc flash computation generator set. This is the loads. This is the short circuit current, the arcing currents, the incident energy En, the arc flash boundaries, the PP class record, the circuit breakers to be used. This is the circuit breaker arcing time. This is the circuit breaker Kaik rating. And finally, we are the group 4, introducing the members. I am Grayson Joshua S. Pruna, the group leader. Jidan Paul T. Alibosa, Shane Benedict D. Barbosa, Arwin Joseph Garcia, Katler M. Manyosa, Jasmine M. Quinto, Luis Antonio R. Reyes, and Joyce Ann A. Veranga, which is presented to Engineer Roland Balansala of E. Condrap. Thank you.